The primary goal of infrared spectroscopy is straightforward. Identify unknown chemical substances by measuring how their molecular bonds interact with light. Molecules are held together by bonds that act like tiny springs. When struck by infrared light, these bonds absorb specific wavelengths of energy, causing them to physically stretch, bend, or twist based on their structure. Because different functional groups, like a carbon-oxygen double bond or an oxygen-hydrogen single bond, absorb different frequencies, measuring that absorption creates a unique, identifiable spectral fingerprint for the compound. The traditional dispersive method of obtaining this fingerprint relied on physical hardware. A prism separated a broadband light beam into individual wavelengths, and a mechanical slit filtered the light, allowing only one single color to pass through the sample at a time, and this created a significant data bottleneck. Measuring every single wavelength sequentially is painstakingly slow, and it severely limits the signal-to-noise ratio of the final reading. To modernize chemical analysis, engineers had to move away from the physical separation of light, shifting the burden from optical hardware to computation. That shift resulted in the modern lab standard, the Fourier Transform Infrared Spectrometer, or FTIR. Instead of scanning one frequency at a time, the FTIR machine shoots all infrared wavelengths through the sample simultaneously. Looking at the system architecture, you can see a broadband source entering the machine. Managing all those overlapping wavelengths at once requires a different physical architecture to encode the light. The process relies on a two-step pipeline. First, the physical hardware encodes the chemical data into a complex wave. Then, advanced mathematics decodes that wave into a readable graph. FTIR trades a simple mechanical filter for a complex mathematical engine, moving the core task of data separation from the hardware to the microchip. The core physical engine handling mixed wavelengths is the Michelson interferometer. As broadband light enters, it hits a central beam splitter, dividing the energy equally down two distinct paths. The first path directs light to a fixed mirror, reflecting the beam back from a constant distance. The second path directs light to a moving mirror. By shifting position, this mirror alters the total distance its beam must travel. When these two separate beams reflect back and recombine at the central beam splitter, one wave has traveled slightly further than the other. The moving mirror exists to force a measurable phase shift between identical beams of light. When the two phase-shifted beams recombine, the laws of wave superposition take over. Their amplitudes mathematically add or cancel each other out depending on their exact alignment. Peak-to-peak alignment creates constructive interference, amplifying the total energy. Peak-to-trough alignment creates destructive interference, dropping the signal's energy towards zero. This chart shows the interferogram. The horizontal axis maps light intensity against moving mirror position, the optical path difference. At zero path difference, wavelengths constructively interfere perfectly, creating the central spike. As the mirror moves, wavelengths fall out of phase, creating the rippling wings. It is a physical, measurable wave that simultaneously encodes the intensity of every single frequency of light present in the broadband source. Once the recombined beam exits the interferometer, it finally passes through the actual chemical sample being tested. While molecular bonds act like harmonic oscillators, their vibrational states are quantized. They can only absorb discrete, specific packets of energy. As the broadband beam travels through the sample, the exact frequencies that match the molecule's specific vibrational states are trapped and removed. The non-matching frequencies pass straight through to the detector. This line graph illustrates how that physical absorption alters the final signal. Comparing the unmodified green baseline with the black sample line, you clearly see how missing frequencies change the precise shape of the interference ripples. The chemical identity of the sample has now been successfully encoded as negative space within the chaotic fluctuations of the interferogram. The detector has recorded the data, but it is just a complex squiggly line mapping intensity to mirror position. Chemists need a graph of individual chemical frequencies. The bridge between those two formats is the Fourier transform. This mathematical function takes a complex signal from the spatial domain and unpacks it. The math reverse engineers the chaotic superposition. It calculates exactly which underlying pure frequencies were missing to create that specific deformed wave. Following the full logical pipeline, the detector records the physical interferogram, the software runs the Fourier transform, and the system outputs the final chemical spectrum. The Fourier transform acts as a mathematical prism, doing computationally what scientists used to do physically with glass. We can map these abstract concepts directly onto the internal chassis of a commercial FTIR spectrometer. The layout tracks the IR source, the interferometer block containing the beam splitter and mirrors, and the final sample compartment located just before the detector. Because FTIR measures all wavelengths simultaneously, rather than scanning them individually, a complete test takes seconds instead of minutes. This efficiency is known as the Feldgate advantage. This speed allows the machine to run dozens of consecutive scans and average them together. Random background noise cancels out, drastically improving the signal-to-noise ratio and revealing minute trace elements. By combining wave physics with mathematical computation, FTIR accelerates chemical analysis, extracting deeper molecular data by removing the limits of